So our second speaker is Murat Sivis. He's a senior researcher at the University of Göttingen in Germany, and also at the Max Planck Institute of Biochemistry in Göttingen. He received his undergraduate education at the University of Göttingen, and his PhD also under the supervision of Klaus Ropers. I first met him when he was working on high harmonic generation from plasmonic nanostructures in the near field with gas phase molecules or gas phase atoms. And I think he was the one that showed that these experiments were dreams, but not real. I think is maybe one way to say it. But in 2016, he came to Ottawa, worked at National Research Council, and looked at high harmonic generation with solid samples, and the dreams became real. Then the harmonics could be made in solid samples with nanoplasmonic devices. So he will speak about nanoplasmonic devices, I believe. So in addition to his interest in solid state harmonics, which is quite a lot, he's worked on also imaging using electrons and accelerating electrons and manipulating electrons with light and capturing spectral and linear and nonlinear properties of optical fields, again, with regards to high harmonic generation. So today he will speak to us on, I believe, harmonic generation in solids. Murat, thank you. It's over to you.
Thank you, Paul, for this very nice introduction. I will share my screen and start the talk right away. Let's start the presentation, I think. Right, I hope you see my screen. Yeah, thank you, Paul, and also Robert, for this invitation to speak at this year's symposium. I feel very honored to be one of the speakers, and I'm glad that I can share you our results on imaging near fields and also possibly in the future high harmonics with ultrafast electron microscopy. So in the preparation of this symposium, Paul asked me what I want to speak about high harmonics. I said I can give a talk about our joint projects where we have looked, as you can see here in this image, at high harmonic generation in structured solids. In this case, it's the third harmonic from silicon, or a recent study where we looked at harmonics from a different solid with tailored fields. But he said it would be more interesting that I give a talk about our efforts in ultrafast electron microscopy, and more particularly in ultrafast transmission electron microscopy, and how we can use this technique that we have developed in Göttingen to map light fields, possibly on ultrafast timescales. And to make this a bit more as a perspective also, I have blended in the end of my talk high harmonics from solids and what we can do with not really high harmonics, but maybe with higher harmonics in the future. So it boils down to two questions that I try to answer in this talk. The first one is, can we quantitatively map near fields of, for example, plasmonic nanostructures by using electrons in a transmission electron microscope? And the second question will be, can we investigate controlled near fields by using multicolor fields and also possibly higher harmonics, or in more general terms, nonlinear processes with this technique? So I will start with this and give you an outline on a short introduction on how this in general works. We use this transmission electron microscope to focus down a beam of electrons which are accelerated to an energy of up to 200 kilo electron volts onto a specimen with a sub-nanometer focus size. I will come to the details in a bit. And raster scan a plasmonic particle which can exhibit a near field. And this near field we can trigger with an optical excitation from outside the microscope and look at the near field distribution and at the intensities. and by looking at the energy of the electrons that are interacting with this light. So how is this working? So the first question that we have to ask is, can electrons, free electrons, interact with a light field? And if you look here at the dispersion curve of a free electron, and particularly in the region of the energies that we are dealing with, you see that this slope of the dispersion curve tells you the rough velocity, or the velocity of the electrons, which is only 0.7 times the speed of light. And if you would now try to shine light onto an electron and make it absorb one photon with the energy h bar omega, you see that there is a momentum mismatch that you cannot overcome in free space. So this is completely different in a scenario where you look at near fields. In a near field scenario, here depicted, the initial electron beam, which has a certain spectral width, in this case something below 1 electron volt, passes this nanostructure and goes through this field, which is confined in space along the trajectory of the electron. This optical excitation is provided from a laser field, and this laser field is confined in space along the along the electron trajectory, as I said, and gives a momentum spread, so to say, a damping of this light field in this confined near field mode, which can overcome this momentum mismatch then and provides delta K momentum that the electron can basically feel the photon. This is a stimulated process where basically one photon is absorbed and the electron will gain one quanta of energy from this photon, this h bar omega. This can happen consecutively, so this can happen multiple times so that you can basically gain multiples of this photon energy. In the same time, this can happen also in a fashion that the electron loses energy to the light field, so that you have basically a cascaded losing of energy, and this results in a final spectrum of the electron where you have gain and loss sidebands separated by the photon energy. In a different representation, in a quantum letter representation, you can also see this as a quantum path interference for certain gain or loss orders, where basically this gain or loss orders can result from different sequences of events. Like, for example, here, I can show you a moment with the show here. If you have the zero loss peak, so the central energy where this initial state of the electrons are, you can basically climb up the ladder with 2 photons absorption and end up in the gain in the second gain order, or you can basically climb one up, another one up, and then one down and end up in this first order, or you can directly go with 1 photon to the first order. And this explains also the shape of this final spectrum here, which is depicted here schematically. So how does this electron energy gain spectroscopy, how it is termed, different from electron loss spectroscopy, electron energy loss spectroscopy, EELS? So in EELS, the electron beam itself acts as a source for the excitation. So the electron is passing with a high velocity for a very short glimpse of time, so to say, delta peak-like excitation, so with a very large spectrum. And this excites all the possible modes that are in this optical or in this plasmonic system, giving rise to basically excitation of all dark and bright modes in the system. And these modes can act back onto the electron, giving rise to loss, which corresponds to basically the resonance frequency of these particular modes. However, compared or in contrast to EELS is a process which happens spontaneously and gives you the intrinsic properties of a plasmonic system or of a material response that you are interested in investigation. EECS, however, can give you the quantitative near field information that you need to basically reconstruct how the field looks like and what the intensity of the field is. In a recent study that we have published this year, we have compared EECS to EELS and also to cathodoluminescence, CL, which is a secondary process of this EELS process where basically the excited modes can emit light into the far field. Besides this capabilities of near field mapping with this method, which I will describe in the resuming of the talk, EECS also happens to be very, very useful in shaping electron beams in time and creating attosecond or sub-femtosecond electron pulses. You can imagine if you have such a broad spectrum with faster and slower electrons and let them propagate, that they will eventually bunch in time after a certain dispersive propagation distance and form a train of attosecond pulses. And in 2017, our group has shown that indeed you can reach something like 650 attosecond electron pulses. The second thing is very strong coupling. In this study, we have used a microsphere resonator where we used the whispering gallery mode resonance and let the electron interact with a phase-matched light field which extended out of this microsphere. The key here is that the velocity of the propagating mode matches the velocity of the electrons. So light can be slower in a material, and in this case, this mode exactly exhibited a phase matching condition such that we could populate over 200 or roughly 250 sidebands and have 700 electron volt wide spectrum in the final state. These are just two examples what we use EECS for. And especially this attosecond pulses are very interesting if you look with regard to detecting higher harmonic radiation, where the process or all the processes also in plasmonic systems occur basically on sub-10 femtosecond timescales. So let us come to the details of the Göttingen ultrafast transmission electron microscope. This is the inner column or a schematic of the inner column of the microscope, and we have modified the microscope such that you can excite the field emitter, which is a Schottky field emitter made out of tungsten, and you can excite this very sharp tip where you usually have thermal electron emission with a femtosecond laser pulse. We operate in the single electron limit to basically rule out Coulomb repulsion that would make our pulses or electron pulses longer in the end. And in this regime, we can reach at the specimen where the electron beam samples our specimen, pulse durations down to 200 femtoseconds. We have a high degree of coherence and can focus our beam down to sub-nanometer level. And for the EECS, we also need a very narrow spectral width of our electrons, so something below 1 electron volt. Additionally, we can pump the specimen with a pump pulse, which is delivered by an optical parametrical amplifier. We can change the wavelength in a certain range from 600 to 1000 nanometers and also manipulate the polarization of the light. So the experiment works like this. We have the initial state, the initial electron state, which propagates down in the column. With a dark field annual detector, we can have a first image of our specimen that we're looking at. So in this case, this nano triangles made out of gold. And this our microscope has the capabilities of a regular TEM. So we can image with thermal electrons. This is an image with thermal electrons, and then cool down the tip and go to the ultrafast mode. Then the final state, as I described before, is given as a superposition of plane wave solutions for these different energies. Here, this Bessel function has basically G as the important factor which determines the coupling between the light and the electron. And this is simply an integral along the way, basically through this light field, and is determined by the amplitude of the light field at the place where the electron goes through. And with this knowledge, or with this formalism, we can raster scan the specimen, do a mode simulation that I will come in a minute, and fit the modes that we are looking at. Here is a selection of X maps that we have recorded. So laser-induced near fields, and then detected with this technique, where G is basically proportional to the width of the spectrum and gives a direct figure for the amplitude of the light field. And this we can do, as I said, for different wavelengths. So how does it work? In the analysis, we look first, in this case, at the plasmonic eigenmodes, so the charge density maps of this plasmonic system, with a boundary integral method. So we calculate by knowing the shape and the outer rim, basically, of this particle. We can calculate very precisely the modes. We have degenerated modes, like the first one. We have corner modes, we have edge modes, and so on. And these modes only depend on the shape of the resonator, not on anything else, like the material composition or so. In the second step, we can decompose the coupling constant into coupling constants of particular modes, and calculate knowing this charge density map, so to say the electromagnetic environment of the particle, the X maps that we should expect if we have an ideal experiment. And with this knowledge, we basically know what are the mode amplitudes. And the mode amplitudes are proportional to, first, the mode frequency, and second, the dipole moment of this mode. And now, by matching the mode frequency and the laser wavelength that we are using, and the dipole moment and the laser polarization that we can set in our experiment, we can easily reconstruct the real modes that are basically contributing to the near fields that we are probing. So here then, the absolute value of this mode amplitude will be the mode population, and the argument will be the mode rephasing. In the experiment, it looks like this. We record an X map, as you can see here. So we have the experimentally retrieved G factor. We extract the geometry of a triangle from a dark field image. We calculate the X maps for the individual modes, and then we use an optimization, so a fitting process, to basically figure out which modes are contributing to our near field that we're creating in the microscope. And this is then the fit. And this fit tells us that the first two modes are contributing, the first two degenerated modes are contributing with different weights. Now, to give or to get a better insight into the real, basically, behavior of this mode, we can do either a wavelength scan or a variation of the polarization. So in this case, I will show you just the variation of the polarization to give you an idea how we can reconstruct the complex mode amplitude. We have, as I said, these two degenerated dipole modes of the resonator that we pump, And in the experiment, we then change the wavelength, not the wavelength, sorry, the polarization direction. As you can see here, X, Y, A, and B are corresponding to two different linear polarizations and elliptical and circular polarization. And the fit is shown here on the other side. And the fit tells us then how are the mode populations for these different polarizations. And as you can see in this bar diagram for the first and the second mode, the first mode for this polarization along the axis of this mode, of this dipole mode, is populated. The other mode is not populated. As you can see here, it's not shining. And if you change the polarization by 90 degrees, you see that it is exactly the other way around. And for circular polarized, it's basically, yeah, both modes are equally populated. And with this, we can, yeah, reconstruct this complex mode amplitudes and represent it on a Bloch sphere. So this is basically a toy model, which gives us the possibility to really investigate the capabilities of our approach, but we think that this can be easily adapted to more complex, not so basically straightforward systems. Okay, this was the part about how we can learn something from electron-light interaction about near fields and plasmonic structures. And now I'm coming to the second part, which involves also the high harmonics. First, the two-color X. I will introduce two-color X for controlling near fields. So if you shine in with one color, you can excite one mode. But if you shine in with two colors and you have two modes to excite, you can basically have a superposition of modes and by controlling the phase, you can basically switch on and off certain areas of this near field. This is a super cool application. A second part is then related to probing higher harmonics, or in more general terms, nonlinear processes. This idea was conveyed by a paper where Klaus was also involved together with Garcia de Bajo, where they predict that by looking at the asymmetry of the electron spectrum, you can probe basically a superposition of the fundamental with the second harmonic or third harmonic that is generated in an optically pumped system. This is the way how the experiment with two color works, for at least in the first part for the plasmonic nanoparticle. We have modified the optical pumping of the specimen by introducing a Mazeltov device, Mazeltov interferometer, which was also was invented by Ofer Kafir, a colleague of us who left us for professorship in Tel Aviv. So you go in with 1030 nanometer femtosecond pulses, focus them down into a BBO crystal, and then superimpose both beams and shine it onto the sample. And with two calcite plates, you can control the timing and dephasing between the two pulses, and a wave plate allows for control of the two polarizations. In the experiment, we sent in this two light pulses, and now the final state looks a bit more complicated. It is asymmetric, and this is simply because of the fact that you have two contributing light fields which lead to a beating and have two different G's. And by controlling, as I said, the phase between these two, you can basically set the asymmetry to one side or the other side. So the population probability is basically just shifted from the gain to the loss side, or vice versa. So in the experiment, we first checked if the modes of the plasmonic particle that we want to basically use in this beating experiment are really what we think they are. Here you see basically the first mode excited with the first frequency, and the simulations and the fit very nicely shows that this is only the one mode that we excite. Then we have the second mode that looks exactly as we think it should look like. So we can pump both modes separately, and then if we pump them together and vary the phase, you see the asymmetry of the electron spectrum, electron energy spectrum, as a function of different dephasing between the two pulses, here in orange and in blue. And this asymmetry of the sideband is then, as I said, controlled with the optical phase. Now we can do a sideband analysis by looking at the sideband filtered images and retrieve basically the shape of the mode by looking into the X maps that we are expecting for these sidebands, or for basically this type of asymmetry for the two different phases, and reconstruct the induced charge distribution for these two color fields. So as you can see here, there's a slight difference. In this case, only this part of the particle glows very bright, and in this scenario for this phase, the hotspot is located more on this side. And this is a proof of concept that you can really control the near field with this two color scheme, and in the same way probe it with X. Now I want to go a step further and talk about the high harmonics. This is, as Paul said in the introduction, subject of great interest for me. And it would be very nice to study also higher harmonics, at least the second or third harmonic, from thin-film crystals. And this is exactly what we are doing in this type of scenario. We did a first experiment on it where we used now BBO thin film and excited with 1030 nanometer femtosecond pulses the second harmonic. This is how the specimen looks like. It is an ion beam thinned piece of BBO crystal, and we park the beam now here in a thin region where enough electrons are still transmitted through the crystal. And when we shine the laser light onto the beam, onto the specimen, you already see here in an image into the sample chamber in the TEM that bright green light emits from this crystal. So this is already a confirmation that we generate second harmonic of this 1030 nanometer light. And now we scanned the polarization of the fundamental, which is so to say a control knob for the relative intensities between the fundamental and the second harmonic, because in this type of second harmonic generation, the two polarizations should be orthogonal to each other. And since the second harmonic is much weaker than the fundamental, and in this two color scheme, both contributions should be almost equal to see this asymmetry. We have tuned the wavelength or the polarization of the fundamental such that we get only very weak X signal, and the second harmonic should give us a strong signal. So we balance basically the contributions of the fundamental and the second harmonic. And as you can see here, you see a clear asymmetry in the electron energy sidebands, where basically the zero loss peak should be located somewhere here. On the loss side, you see basically more population than on the gain side. And this fits quite well with this prediction here from the paper from 2020. So with this, I want to conclude. I've shown you that we can probe in a very nice and elegant way complex fields with by using electron microscopy, ultrafast electron microscopy, and possibly in the future with also sub-femto, or let's say few femtosecond temporal resolution and on nanometric length scale. And also the outlook is given for probing nonlinear processes such as high harmonic generation in solids. I have to thank a lot of people, especially the UTEM, the Göttingen UTEM team, which comprises excellent set of excellent researchers. And particular, I have to acknowledge Hugo Lorenzo Martins, who is a postdoc from France in our group for quite some time now. And he did this experiments together with me, and he's also responsible for all the theory that is behind this plasmonic near field reconstruction. And also I have to thank my boss and supervisor, Klaus Ropas, who's the head of the group in Göttingen. I thank you for your attention, and I'm really gracious, and it's a pleasure for me to be here and speak to you.
Thank you very much. And Jeremy will handle the question period.
Yes, thank you, Paul, and thank you, Professor Sivis. First question is, you discussed measuring the plasmonic structure, but what about the substrate? How did you deal with the substrate experimentally?
Yeah, you can, in these experiments, you can neglect the substrate, because this is the beauty, I think, of this experiment, because the X comes predominantly from the specimen. It will, of course, affect somehow how the specimen behaves, but this is exactly what you want to know, because if you just would go and say, okay, I don't need to calculate, or I can just simply calculate, then it gets complicated for the real distribution of the near field, because then you really have to know how this coupling works, right? If you have, for example, silicon nitride substrate below it, and put your particle on it, what are the boundary conditions for the simulation there? Our X method really tells you how the real near field looks like, and that is the beauty about it. So it gives you already everything, plus the coupling to the substrate, and all the basic imperfections that you have maybe in the specimen itself.
Thank you. Next question. Would you please give an outlook toward isolated attosecond electron pulses, mainly the technical advancements and challenges?
Okay. So this attosecond experiments that I was talking about, they are delicate in a way that you have to have basically first to create this energy spectrum. This is maybe not the hardest part, and then let it propagate. In the detection scheme, we have then a second interaction of the same sort, and you can basically reconstruct the attosecond plot structure by looking at the Wigner distribution of the electrons when you have this interaction. This is possible. The harder part is, I think, that you will still have a lot of electrons which are not going through this interaction process, for example. So you will have a lot of noise. So in order to get very clean attosecond pulses, you basically have to have multiple interactions, for example. This is one. And the second is that you always get a train of attosecond pulses. So that limits basically what you can look at in the end. So you will not easily achieve a scenario where you have a single attosecond electron pulse. So you will always have a form of attosecond pulses, and therefore you have to have a system where you can basically use such a comb.
Gotcha. Thank you. Now a more technical question. What is the distance between the mirror and the sample position? And is the mirror itself flat?
Yes, the mirror, we have basically two types of excitation for the so you mean the optical excitation of the specimen, right?
I think so, yes.
Exactly. So one is directly from the side. So there we have a lens from outside the microscope, and the distance of this lens, and there's a mirror in between, is something like, I think, 25 centimeters. So it's located outside of the microscope. So where you have basically a side of view, a side of line, basically a line of sight, sorry, onto the specimen. And in this top excitation, I think it's something like several centimeters. I have to lie, but in that range. So
Thank you. That is oh, I have one more question that just popped up. 1 second, please. Why is the near field enhanced in the center of these triangular nanoantennas rather than at the edges? In the first slide where you showed the field on the nanoantennas, also in circular polarization, why is the near field enhanced at the 3 edges?
okay, first of all, we can go through the through the specimen, and we can see the central hotspot, but this occurs at a very different energy. So the core, basically the core mode, is at a different energy than where we are probing. So the modes that we are looking at here for this particular wavelengths are the edge modes.
Okay, so your frequency is selecting particular
Yes.
modes.
Exactly.
Gotcha. Thank you. Thank you very much. That finishes our question period. And once again, thank you very much to Professor Sivis for his fascinating talk. Thank you.
I think it's over to me, and I also want to extend my thanks to both speakers, but particularly Murat, because he's the last of the 2 speakers, for wonderful talks today. And I want to invite everyone in the audience to come to the poster session. I think you will also find that very interesting. And the posters will be open for quite some time. It's a different link. I think it's been sent to you. It's also on the website. So it's a different link, but it's to Zoom rooms. And there you can join one room and treat it like a poster. Ask any questions you want to the student that's presenting the poster, and then go out to another poster in another Zoom room. So thank you very
Paul,
much
for having me. And
thank you. And I might send you another question afterwards. I decided I would only ask one. I send you a second though, Eric.
Okay.
Okay. And thank you very much. And I'll see you tomorrow, or I'll see you at the poster session. Goodbye.